All right. Thank you so much. Thank you very much for having us. Hey, everyone. My name is Wes Floyd, and today we're going to talk about EigenLayer, and we're going to go as deep on the tech as we possibly can. I want to give you guys, start with a very high level. What is EigenLayer? What is an AVS? Why would you want to build an AVS? And then we'll go deeper into some technical architecture and also show you guys a demo. So if you want to just run a basic AVS, build your own, you've got the tools. All right, so if you need the slides, please scan this QR code. I'll have this up here as well. And just by way of intro, so I'm a member of the DevRel team at EigenLayer, and please follow us at Build on Eigen. We've got a bunch of folks from our team here this week. There's a bunch of hackathons going on, and always seem like in parallel. So please follow us if you want to get involved and get hands-on and actually building out your AVS. A little bit of background in my context. I spent a lot of my career doing solution engineer DevRel work in traditional Web 2, decentralized systems or distributed systems and cloud, and was also mining Ethereum in the evening. But over the past couple of years, I've been very passionate about decentralized infrastructure, decentralized compute, and making that available for Web3. So over the past year, I've been at EigenLayer, and I've been able to help actually work with AVS teams to build this out. And I think that EigenLayer shared security is a really helpful base layer for anyone who's building in Web3. And so that's what this talk is about, is how we can help your project by adding EigenLayer with shared security. All right, so let's just give a quick overview of what EigenLayer is, and even like why would you even care about building an AVS? So there's a couple common problems in Web3 that we want to be able to help with. The first is access to economic security. And people talk about decentralization as a very broad term. One way to quantify decentralization is how secure is your app? How much capital do you have securing your app? In case if you're going to launch a new L1 or a new dApp and something goes wrong, how much are your users compensated, or how much are they disincentivized for people to hack that? And so with EigenLayer and restaking, we make a significant amount of that economic security available for anyone who's building a dApp. You can tap into that. It's shared security. It's available for folks. And it's pooled across different AVSs. The second one is for new tokens that are launching from scratch and they want to secure their network. Like if I want to launch Westcoin, it's going to be the new AI app. People are going to have to purchase Westcoin, and the TVL is going to have to grow over time, but it starts at a very small amount. So how do you bootstrap a net new network with economic security? One of the really powerful things that EigenLayer is offering is dual token or multi-token staking, so that your users, when they are providing economic security for your app, they can stake both native ETH and also your token at the same time. So you can have a steady growth in token value accrual and still have the benefit of the larger economic pool of broader Ethereum from restaking. The third is bootstrapping an operator network. It's very difficult to bootstrap a network of operators. If I'm launching a new coin, Westcoin, this new AI token, and I want everybody to be an operator to actually run the inference on the AI network, I have to go out and have to market to people, and I say, hey, please be a validator or operator on Westcoin token and get started. And I have to all these incentives. It's a lot of work to recruit these folks. On the EigenLayer network, if you go to app.eigenlayer.xyz, we have hundreds of operators that are ready to run these AVS services. All you have to do is plug in and provide the means for them to run your AVS service, and they're ready to go. So it's a massive accelerator for building your application. And the last is layering decentralized trust. Most Web3 projects have some sort of a roadmap for decentralization, and we really want to support projects on that roadmap, or if they're building from scratch. Decentralization is important, both from a security perspective, from a policy perspective, or philosophically for your users. But building decentralized systems is very difficult. And so what I want to show you guys today from a technical perspective is think about all the benefits of your current architecture and how you'd like to build your app as it is, and how you can just add EigenLayer as a +1 to that. So we're going to talk about different ways to establish trust, through rewards and slashing. We'll talk about objective attribution, which is available now, rewards and slashing coming soon. And then very recently there was the Eigen white paper, Eigen token white paper was released. This is back in, I think, late April, early May. And the Eigen token white paper talks about a different way to verify Web3 projects, which is through intersubjective agreement. And it's a really powerful primitive, so we'll talk about that here in just a second when we get to trust modeling. All right, so just starting at the most basic layer, what is EigenLayer and how does it work? So in this diagram here, we've got three people. We've got Robert. Robert is a restaker. Robert, thank you, Robert. Thank you for restaking. Robert brings his capital. Capital is critical because it establishes trust. It is the economic sort of underlying base that we're talking about. And we also have folks who are professional operators. You know, in Ethereum and other ecosystems, there's always been folks who are they're very good at operations. They have data centers, they have good uptime, they have good DevOps people. They're professionals at this. Or maybe it's a solo staker operator. It could be that for decentralization purposes. And then Ava is a developer. She's got the brains. Ava knows how to build that smart new AI or database project. They know how to build the services, but they may not have capital themselves. They may not have the operator network yet. So EigenLayer is all about bringing these three parties together in a nice, convenient marketplace. Robert, the restaker, whoever that restaker is, could be a person running an ETH node, ETH validator, could be someone bringing an LST like Lido or Frax or something like this. Robert is going to delegate all of that capital to the operator. So they're going to say, hey, I'm going to give you this capital. I'm going to give you ownership or delegation rights to this state capital. The operator is then going to choose some series, one or more AVSs to run. Olivia might run Ava's AVS. Olivia might run my AVS. Olivia may run a few other interesting AVSs, maybe a roll-up, something else like that. But that trust is going to be established with the operator. And so this is how the market is going to start. The operator is going to opt into the service, and then they're going to offer it to the end user. So looking at this as a bit of a stack, everything about EigenLayer resolves back to Ethereum L1. We are going to be doing some work to support L2s in the future, but initially it's all around the base layer of Ethereum mainnet. We talked about stakers, operators, and developers, and then AVS consumers is an important category. It would be anyone who's actually using the service. So if I'm calling Ava's AI service and I need to do some inference, I'm a consumer of that service. And the goal over time is to have it such that these AVSs are like Lego bricks and you can plug them in. So if I'm coming into the ecosystem and I need to build a new application, someone has probably built an AI application, someone has probably built a database application. I can reuse their services to build my larger new service that I'm going to build. And then lastly, EigenLayer governance is important. We just launched the EigenLayer Foundation about a month and a half ago, and so it's a new organization that's being built out, and it's all about decentralizing the protocol itself. There's a term that our CEO, Sriram Kannan, uses often, which is shared security, and it's somewhat a new term, but I think of it very similar to the benefits of decentralization. When someone says, I want to be decentralized, part of the reason for being decentralized is so that you do not have a single point of failure. And so let's look at what it looks like to have unshared security prior to EigenLayer, what these services would have faced. So if I'm wanting to build my service, I have to build my own operator network, I have to build my own capital base, and I'm really isolated into my own world. There's difficulty and overlap between these various systems, different L1s or different app chains. They don't have interconnectivity. They don't have sharing of capital or operators. And the same is true for all the other services. So you have this isolation. Inefficient use of capital. It's more expensive for each network to boot up their network, and then it takes time to boot up the operators. In a shared economic security model, you have a pooled set of capital, which is this restaked LST. It's available for everyone to build their services on, and the operator network is also available for everyone to build on. So we talk about benefits of shared security in general. This is a way to sort of visualize how all that comes together. And right now there's a bunch of different teams. If you go to app.eigenlayer.xyz, you can see all the different AVSs that are being built out and launched on mainnet. Initially, EigenLayer spends a lot of time, some of the early AVSs are around Ethereum-centric services, roll-up services, MEV, bridges, decentralized sequencing. But going forward, there's a big interest in serving consumer applications, so social media, gaming, all these different verticals. And so people that are building in those verticals, they need other primitives. They need execution for AI purposes. They need a database. They need ZK provers. So you see these other coprocessor categories here becoming very important. We're building out things like folks that offer TE networks, fully homomorphic encryption. So the goal is that if I want to build a dApp, I can come to this marketplace and I can take advantage of all these services that are already built out. And then it's also helpful to call out EigenDA is one AVS that we are also building in-house. We're building it as an example of how to build a very complex, full-featured AVS. But it's also built to service the data availability market. L2 rollups need high quality, high throughput data availability. And so that's one that we're launching. Yeah, and so if you go to our website, app.eigenlayer.xyz, you can see live all the different AVSs that are launched on mainnet here. And this is the goal, is to support people eventually launching to mainnet. All right, so let's get into trust modeling, because this is sort of a new concept that exists in AVS that doesn't exist in the Web 2 world. If you think about existing Web 2 systems, they're very much trusted systems. If you build an app, you're going to run on AWS, Microsoft, you trust the platform, you trust the infrastructure. In Web 3, the systems are trustless. Like Bitcoin operates on its own, the algorithm validates itself, you do not have to have trust in the operators. In this new world, with AVSs, we had to think about a new dimension, which is how do you model that trust? And based on your app, you'll probably need to model trust in different ways. So to give you an example, let's see if I can, oops. Let's see if I can get this diagram to load here. Okay. Okay, well, that's not loading. Well, I'll give you the narration anyways of what the diagram should look like. So if you think about the typical Web 2 stack, there are a few different components here. You have compute, you have storage, you have networking, you have database, you have messaging, and those are all assumed to run on their own independently. And you have trust. These are opportunities to establish anchor points for trust as you're building your AVS. So there's a couple different types of trust that can be established for an AVS. The first is objectively attributable. Objectively attributable is something that can be very easily proven on chain. So for example, someone runs an algorithm off chain and they have a ZK proof. They can write that ZK proof on chain. It's very easy to establish it. In this world of shared security, that can be used for slashing someone's stake or for paying a reward to someone for operating correctly. There's a different type of truth. So we can look at the room right now. We can say, oh, this room has tall ceilings. We all kind of agree this is a room with tall ceilings. But that is somewhat difficult to prove on chain, even if we all have a consensus about this, that this is the case. So it's a subjective opinion, but it's a subjective opinion that we all agree with amongst ourselves. It's intersubjective. This has been a very difficult thing for us to capture on chain, but if you look at the latest Eigen token white paper, this is really a big part of the topic, is how can you get the benefits of things that need to be agreed upon in the real world off chain, but then have a mechanism to validate and prove those on chain. And so if you look at things like Oracle price inputs, data availability, AI inference, so if I ask the AI to generate a picture of a dog, if it looks like a cat, but that's sort of a subjective opinion, this will open up a lot of opportunities for us to validate these other AVS services on chain. And so as you're building your AVS, you want to think through a few different things. How much economic trust do you need? If your AVS is supporting Oracle bridges that have $1 billion in TVL, you might need a lot of economic trust. You might need to tap in a lot of that for your operators. If you're doing AI inference that generates cat images, you may not need as much economic trust. Maybe $1,000 is enough, so you have to think about how much is important for you. Which components in your project require trust? In a broad architecture, I'll show you guys in just a second, like EigenDA, some parts can be trusted and some parts need to be validated. So think about which components. Also think about from your user's perspective, they may care more about certain aspects of your application to be proven. And then lastly, what type of proving is required, objective versus intersubjective. Let's see if I can show this diagram anyways. No, it's not going to work. Okay, well, let me just see here. Let me see if I can get a different set of slides to load. There we go. All right, so this is an example of an AVS, trust architecture being built out. EigenDA is the AVS that we're building in-house, and it's specifically to service these roll-up sequencers here. So if you think about an L2 network, all of this living up here, the roll-up sequencer is sort of the heart of the L2. It's where all the transactions come in, and those transactions today, in absence of a data availability layer, are written on-chain to the L1. So the roll-up sequencer is batching all these transactions into a blob and is writing to the L1. In this new world with the EigenDA AVS, it writes it to a disperser. This EigenDA disperser component here takes all of those blobs from the L2 and writes it into each individual operator. It batches them into a group called a chunk. It creates a KZG commitment scheme and sends them to the operator. The operator then signs for their chunk of the data and sends it back to the disperser. Each of those signatures from the operators are then written back on chain to Ethereum in the EigenDA AVS contracts here. And that signature from all those operators is then used for slashing in the future, rewards payments to the operator. This is the on-chain provable data set. It's actually a piece of data that you can inspect and you can query and you can say how many of these operators actually wrote that specific piece of data back online. And that is the trustless aspect of EigenDA. And so that's an example of how to build an AVS. I'll just pause to see if you guys have any questions about this architecture. If not, I can keep moving on. Okay. Hey, please, yeah.
So you said that like the transactions from the rollup, they're going into this EigenDA disperser, the sidecar, and then they're being somehow like batched again into different EigenDA operators. What are those? Are those like nodes running somewhere?
Yes. No, thank you for calling that out. This is something worth kind of clarifying, is that when you build an AVS, what you're really building is a piece of software that all of those operators are going to run together. So in this case, each of these operators here are running nodes for the AVS. They're running the EigenDA AVS software. And they're sitting there listening for any activity to be sent to them from the disperser. And they'll get a request from the disperser, say, hey, here's a chunk of transactions in the blob itself, or the chunks of the blob. Sign that you have actually received this, and sign me a commitment and a signature that you've correctly stored it, and then send that signature proof back to me, the disperser.
So it's some sort of sharding kind of.
It's exactly sharding. Yes, thank you. Yeah. No, I'm glad you asked, because I don't want to go too much detail that you guys might not be interested in, but that's really the special thing here, is that in order to reduce the cost substantially for rollups to write their data availability layer, like writing to L1 and ETH is very expensive, writing to EigenDA is very inexpensive, and the throughput is much higher. The way they accomplish that is they take these large series of blobs coming in from the sequencer, they batch them into a chunk, and they write pieces of those chunks to various operators. So these operators don't necessarily have to know which blob they're storing per se, they just get requests. They're just kind of a simple response mechanism from the disperser. But what that allows us to do is it's sharding effectively. I think they use Solomon Reed encoding as the specific algorithm they use. So like one chunk of data might be split into multiple pieces, and those pieces might be written to a couple different operators in the network for backup and availability purposes. So this is kind of the first iteration. This is objectively provable on chain. There's another interesting aspect of this architecture, which we're going to be spending a lot of time on in the future, which is intersubjective agreement. So if I'm this rollup sequencer over here later on, and someone says, I want to initiate a fraud proof, something that happened in the L2 is wrong, and I think this blob and the data set, the transactions are totally invalid. Normally what you do is you go to the data availability layer, the disperser and these operators here, and you say, I need to retrieve a copy of that blob because I want to inspect it. We're going to have a fraud proof. It's very difficult to prove on-chain whether or not these operators are returning the data to the end user. You can test it. You can test yourself and say, hey, can I get the data? You can have individual testing. You can have committees of people that do this, data availability committees that do this. But it's sort of a subjective thing. Did it work for you? Did it work for me? Did it fail at a given point in time? And this is a good example of this intersubjective agreement that's going to be a big part of the Eigen token as its functionality gets released, so that we'll be able to prove what's called custody. Not only are we now proving that the data was stored, we'll also be able to prove that the data was being returned to the users. So that's a big next step for the future of the EigenDA AVS. All right. So let me just give you guys a brief view of our Hello World AVS. I think this is a good place to kind of help you guys launch as you're thinking about building your own AVS. Can I just do a quick time check? Robert, how are we doing on time? 10 minutes? Okay, cool, perfect. So I'll be quick through this and save some time in case you guys have questions. I do want to point you to the EigenLayer documentation here so that you can go visit docs.eigenlayer.xyz, check out our AVS development content here. And in particular, this section I think is particularly interesting, which is what are the minimum requirements to build an AVS? There's some work that needs to be done on-chain, integrating with the smart contracts. You integrate with the EigenLayer core contracts here, the AVS directory, and you have to submit at least one event on-chain. You have to submit something that can be proven verifiable on-chain. That's totally up to you, what it is, what it represents. This is a big open canvas for you to paint and think about designing some fun stuff. Off-chain, for the operators, the operator has to register to the AVS, and then the operator does need to send some event on-chain that can be proven. That event off-chain could represent anything. It could represent an EigenDA, that the data was stored properly. It could represent that there was a ZK provable computation that was performed. It could represent that there's some Oracle price. This is all where you guys get to be creative in building your AVS. And then on starting your first AVS here, we have a Hello World example, and I'll just show you a couple very brief walkthrough of this AVS. This is meant to be the minimum viable AVS that you could possibly build, and it does a very simple thing. There's a consumer, there's some off-chain service here that sends an event to the contract on-chain. It says, say, hello world, I need you to emit hello world with some random name, and that's a task. That task exists here on the AVS contract. The operator is listening. It's waiting for that event to be written, and when it sees the event, it says, okay, I'll take the task, I'll go off-chain, I will write that hello world example off-chain, and then I'll write a signature back on-chain to prove that I did, in fact, generate that string. And so this is a code base that you can actually go to right now, and you can fork, and you can run it. And you can also modify it. You can kind of get in there and you can change the behavior of the operator. Instead of just emitting a string, you could have it trigger an AI inference or whatever is relevant for your specific project. But you can think of this as sort of a scaffolding to get started. And I'll just very, very briefly jump into the code base here. We've got a couple of different implementations. We have a Rust implementation here under the operator folder. We also have a TypeScript implementation here. In this case here, it's calling a couple simple functions that look familiar. Register the operator, sign and respond to task. When it hears the tasks on-chain, it's listening to that task. And then the contracts folder here, this is a very standard Foundry layout for the code. We've got a simple AVS implementation here. Hello World Service Manager. And then under the scripts here, we've got a lot of deployment code to deploy that code along with other AVS bits as well. And so I'll see if I can just give you guys a very quick demo of what this looks like running live. So what we're going to do first is we are going to start up an Anvil chain, and that's just going to be a generic Anvil chain. But we're also going to load all the EigenLayer contracts. All the stake registries and the operator registries are going to be sitting there waiting. And then on this other terminal window here, we're going to start the operator. So it's going to be listening for new tasks. It's going to go and register the AVS. It's going to listen. It's going to hear what's going on. There's a task waiting for it now, which says, hello, EigenWorld. And then over here, we're going to start the consumer. We're going to say this person is just going to spam tasks. It's going to send a request on chain to create a new task. And when it gets the new task, it's going to detect that, and it's going to generate that task on chain. And you'll see that happen here in the off-chain code right there, or in the Anvil chain. So that demo is available for you guys to run online. And then in terms of next steps, that's pretty much all we had today. Please check us out if you'd like to build any of the hackathons. If you have any questions, I'd be happy to help answer them. And thank you for letting us present today. We appreciate it.
Great. Any questions from the public? If not,
Yeah, thank you for presenting all of this. So I just want to ask, as a builder, so what is the simplest but real world, like real AVS that was developed on EigenLayer? Because a lot of AVS, they are quite complicated. And the question is, okay, is there something simple which gains a lot of value from EigenLayer being something simple at the same time? Do you have some example?
That's a good question. Something that's simple, and a simple AVS that was built on EigenLayer that provides...
Yeah, but has some real, product, not like a test one, but something that can be utilized in real world.
Yes.
Can have users and stuff, yeah.
Yes, absolutely. Excellent question. And let's just segue here. These are all systems that I think are getting usage right now. We don't actually track the amount of usage from each of those, but one in particular that I have some more firsthand experience is EigenLayer. They're a restaked rollup, and they're also building their rollups to be AVSs at the same time, so they're getting a lot of activity from L2s. Simplicity is a little bit it's a bit hard to come by. Each of these has their own complexities to them, so some of them are like varying levels of complexity. I would say the other one that's more simple maybe is there's a really good videos about Lagrange as a ZK prover network off chain, and that one they did a really good talk on our YouTube channel that goes over their architecture. That might be a more most straightforward architecture to reference to start.
Yeah, because I think that for EigenLayer is very important to show something simple that can be built without EigenLayer but wouldn't have any trust, right? So, and you can say, okay, you can build this in 1 week, and you can build this in 1 week on EigenLayer, but get real trust, real users, and get the results, yeah.
Well said. Trust. I mean, that's at the end of the day. That's what it's all about, is building that trust in decentralized systems.
Thank you.
Yeah. Thank you.
thank you very much. Any questions?
So if I need an ABS, if I want to create an ABS, I need to define the code of the tasks. How do I define the task? Is a code in some language? In Rust, in whatever language, what is supported right now?
Great question. So if you want to define a task for an AVS, what language can you use? It can be any language. It can be Rust, Go. We actually support Rust and Go as kind of first top-level citizens. We have SDKs for them. But you could write it in TypeScript. I've written one in JavaScript. You could do it in Bash. Anything that can be executed off-chain but writes an event on-chain is good to go.
Do I need to write as well the validation for my task? Or because you mentioned that the operator is going to push a proof that he executes the task. Mm-hmm. But how is that proof generation associated to my task? How it relates is my question.
Yes. How, just to replay the question, you're saying operator's going to do some work, they're going to submit a proof on chain. How is that proof validated effectively?
How it's created and how I can validate it as well. I created the task, but how can I ensure that there is a way that my task can be validated?
Well, so that is partly that is the creative space for the AVS developer to determine how their task needs to be validated, and it will vary a lot depending on the topic or the area. Like for example, some people want to verify identity, or some people want to verify Oracle price or some other mechanism. So there's a little bit of creativity into thinking through that. We are working on a component called slashing, which is coming up soon in the protocol. Slashing is very important because all of that stake that is staked into your AVS, if the operator misbehaves, their delegated stake can be slashed by a certain amount. We haven't released the specific designs for how the slashing mechanism works yet. So there's a little bit more work to do before those slashing goes live. So we don't have like details on that yet. But what we do see is there's other mechanisms you can use today. So for like an EigenDA, if a operator stops responding, they just go offline, you can eject them from the operator set so that they're no longer an operator in your network. There's a couple mechanisms to help out with that in the meantime. Yeah.
Thank you.
Yeah, cool.
And I think we can take a quick question. So.
Yeah, I'll be quick. I have two simple questions regarding the architecture you presented. The first one is I want to know what do you mean by the erasure coding?
Yeah.
Yeah. The second one is that when you split the data task into different chunks, and then different chunks will be processed by the operator. So my question is, will the operator deal with the same data, or is like the data chunk being computed by the operator? Do they have overlaps?
Oh, is there overlaps
Yeah.
within the data for the operator?
Yeah.
Yeah. Let me give you an example of that because this might be applicable for other AVSs. What happens is the rollup sequencer is writing blob files, I think 2 megabyte blobs, something like this. The disperser will batch those blobs up into a chunk. The chunk is kind of the unit of measure of data for the system. The chunk itself is divided into smaller portions, and each smaller portion is written to multiple operators. I think maybe 3, 4, 5. I don't know the exact number. But it's written to enough of them such that if any one operator goes down in the network, the other pieces of the data can help reassemble the overall data set. And it uses a technique called erasure encoding, which is, I think it's like Reed-Solomon is the name of the specific algorithm that it uses. I think it's pretty popular from a number of other algorithms. So it's basically a recovery mechanism so that we're writing as little as possible, and that is a big scaling mechanism for DA. But yeah, thanks. Cool.